Hello, how are you?
Hello, I'm good. How are you?
One second, I think my volume is off. Okay, now I can hear you.
I'm good. How are you?
I'm all right. I guess we got 5 minutes. Just
Yeah.
been preparing the class. What other stuff are you taking any other math classes?
Yeah, I'm in non-commutative algebra and I'm doing this reading course on quantum groups.
Okay. So are you like a hardcore algebraist?
I'm into representation theory and um, lead theory. That's the direction I guess I'm most familiar with. So um, yeah,
There's a lot of great representation theory around MIT. I
yeah.
think it's the world center for that. Hmm. So remind me, are you a undergrad or a grad student?
I'm a grad student, second year grad student.
Know who you're gonna work with?
Yeah, Pavel Eddinghoff.
Okay, that's good. More people here now. Hello, everyone. What are your other classes doing to sort of handle the fact that everybody's virtual? Are people doing like online icebreakers, or are they not really doing very much?
I think it's mostly just encouraging that we collaborate outside of class. But I think this class has done like probably a better job at encouraging that than the others I've been in.
Okay, I'm not sure that I did very much, but we'll try here. Yeah, so hopefully you guys have all signed up for the PSET Partners website. I know there was a lot of work put into it. I hope it works. If it doesn't work out very well, then we'll talk about other ways to pair people up. So nobody has like a green screen with a meme or something behind them, dude. I sort of hope to be like more entertained by people's backgrounds than I have been. All right, very good. I would encourage everyone to entertain each other with weird backgrounds if possible. All right, hello everybody. So by my computer's reckoning, it's 11:05 now. So just one announcement is that I've posted here the first P set. So if you go to assignments on the Canvas webpage, you'll be able to see problem set 1. And you can click this to download the problem set, and you'll submit your problem set online here. And it'll be due by September 18th class time, so about 2 weeks from now, a little over 2 weeks from now. So again, if you aren't yet signed up for this website, PSET Partners, I really recommend it. You can see a lot of you have already signed up. I think you have to sign up by today in order to get into the matching for this class, at least the first round of matching. So sign up for that soon if you haven't already. If it doesn't work out and doesn't help you find a group to do the PSET with, please talk to me and we'll try to figure out something we can do, because I know this is a new website and I'm not yet sure how well it will work, but hopefully it'll work well because there was a lot of effort put into it. Right, so that's the first PSET. That's the main thing. Of course, recommend you start doing the PSET right away, because if you do the problems which make sense, given the things we've talked about, some of them won't until we talk about a few more things. But if you do the ones that make sense, then it'll help you absorb the material as we're going along, rather than waiting till 2 weeks from now to do it. Okay, so let's get started then. I'll try to do it. All right, so hopefully you can all now see the iPad. Okay, so then just to repeat a few announcements, PSET 1 is posted. Go do that, get familiar with it, and get started with it. Hopefully you'll have some groups set up by the end of today with that website. Another announcement is that there's no class this Monday, I believe, because of Labor Day. So the next class will be Wednesday. And then office hours will be today after class. But starting next week, in order to accommodate some people from other time zones, they will be the hour before class instead of after class on Wednesday and Friday. And I'll post an announcement about these office hours on the Canvas webpage. I'll also try to finalize the date of that little exam, which will just be worth a small percent of your grade, but I'll try to finalize that date by next week. Okay, so let's get back into the math then. As always, feel free to ask any questions at any time, just unmute yourself. So what did we do last class? We learned how to compute the first homology group, H1, of G, basically when G is a directed graph, or a kind of thing that had some vertices and then some arrows with direction, a sort of combinatorial gadget. And this first homology group somehow measured something about the number of loops in the graph. So let's just do yet another example so that we can use it as a launching off point. Maybe our graph will look something like this. Here's A, B, and C, the 3 vertices, and then F, G, and H, the three edges. So if this is my graph, then how do I calculate the homology, well, I form the map of abelian groups, the free abelian groups. Map just means homomorphism. And I'm going to go from the free abelian group on the edges to the free abelian group on the vertices. And the map is just defined by where it takes the generators of this free abelian group on the edges. It's going to take F to B minus A. It's going to take G to C minus B. It's going to take H to C minus A, where here I'm always using the target of the arrow minus the source of the arrow. Okay, so note that a purely algebraic question now is to compute the kernel of this map of free abelian groups. And maybe I'll call this map boundary or partial. Sometimes I might call it D, sometimes I might call it partial. But in any case, every class in the kernel of this boundary operator is a multiple of G minus H plus F. You can see that that linear combination of G, H, and F is mapping to 0, and then maybe it's an exercise to check that anything mapping to 0 will be an integer times G minus H plus F. Okay, and then given that, we know now that this first homology group, which is by definition the kernel of this boundary homomorphism, is just the free abelian group generated by G minus H plus F. And the fact that it has one generator is related to the fact that in this picture of the graph, there's sort of one loop or hole. Okay, so that was last time, but there were two problems that we highlighted last time that we're going to try to talk about solving today and over the next few classes. So the first problem is we want to handle higher dimensions. I want to be able to talk about even say like 100-dimensional or even an infinite dimensional object, higher dimensional objects, not just these sort of one-dimensional graphs. And secondly, we want to handle topological spaces. Things like subspaces of Rn, and not just combinatorial objects like directed graphs. So we'll talk about each of these problems in turn. Let's focus first on problem one, this question of how we can start to study higher dimensional objects. So what I'd like to do is introduce the basic sort of combinatorial representation of a higher dimensional object in algebraic topology. So the sort of one-dimensional version is a graph, and now I want to talk about the higher dimensional version of a graph, but something still essentially combinatorial or finite. So let's look at one example before we do the general definition. So here's one higher dimensional example. So I'm going to draw the same picture I drew previously with 3 vertices, A, B, and C, 3 edges, F, G, and H. Hard for me to draw a straight line. And now I'm going to imagine that we want to sort of glue in a triangle, which I'll call capital A. So I'm imagining that we're gluing in a sort of 2-dimensional triangle now. So I'll be precise about this in a moment when I give the general definition, but let me give you sort of a picture of how to think about this. So now that we've glued in a sort of solid filling of this loop, it should no longer count as a loop. So we sort of expect H1 to be 0 now. There is no longer a sort of a hole in this solid triangle. So the way that this gets expressed is that G minus H plus F is still going to be what's called a cycle. So it's still going to be in the kernel of some kind of boundary operator. But it is also in the image of some kind of boundary operator. In particular, the boundary of A, this sort of two-dimensional object, is going to equal G minus H plus F. Because if I walk around the boundary of A, you could see, for example, I could start at B, move along G, move backwards along H, and then move forwards along F, and I've walked along the boundary of A. So in general, what homology is going to record are these cycles, or sort of potential holes, modulo the boundaries, or holes that can be filled. So let me give now a rigorous definition of the combinatorial gadgets that one obtains by gluing together points, edges, triangles, tetrahedra. In general, you're going to be gluing together sort of higher dimensional versions of triangles, which are sometimes called simplices. Okay, so what's the basic combinatorial gadget? A semi-simplicial set, they're called. A semi-simplicial set X is a sequence of sets there's a set x0, x1, x2, x3, on and on forever. And they're going to be functions. There's going to be a function called d0 and a function called d1 from x1 to x0. It's going to be a function called d0, a function called d1, and a function called d2 from x2 to x1. And then in general, there's going to be n+1 functions that go from xn to xn minus 1. And that's going to be true for every n greater than or equal to 1. Okay, so it's just a set and then a huge collection of functions between, or it's a sequence of sets and a huge collection of functions between the sets and the sequence. And these functions are not totally arbitrary. They're required to satisfy a condition. They're required to satisfy the so-called simplicial identities. Which say that di composed with dj is equal to dj minus 1 di whenever I is less than j, and that expression makes sense. Okay, so that's it. I will try to indicate some examples, and then you'll hopefully get some practice working with these things on your homework. But this is the basic combinatorial data that defines an arbitrarily high dimensional thing built out of triangles, essentially, built out of vertices, edges, triangles, tetrahedra, and then higher dimensional versions thereof. So let's look at some examples. So suppose I'm thinking about a semi-simplicial set. In which most of the sets involved, like x2, x3, etc., are all empty. So I'm imagining that the only possibly non-empty sets are x0 and x1. So such a thing is just a directed graph. Right? What is it? There's two interesting sets, x0 and x1. And you can think of this as the set of vertices, and this as the set of edges. And then there are only two interesting functions. There's d0 from x1 to x0, and there's d1 from x1 to x0. And this function records the target of an edge, and this records the source. And then as long as x2 is empty, x3 is empty, etc., the simplicial identities don't say anything. They turn out to just be automatically satisfied. So directed graph is just a very special case of a semi-simplicial set where we don't have any two-dimensional or higher data. Let's do this other example that we sort of indicated a little bit about earlier on. Maybe we imagine some simplicial set with three vertices, A, B, and C, three edges, F, G, and H, and then a single sort of two-simplex, which I might call capital A. So if I am trying to write this down in a form that can be read by a computer, I'll just say, okay, x2 should be a set containing only one object, A. That's the unique triangle. x1 would be a set with three objects, F, G, and H, the three edges. x0 would be the set of A, B, and C, the three vertices. Okay, now I have to specify a whole bunch of functions, right? I have to specify, right, and I'm going to say x3 is empty, x4 is empty, etc. There's no higher dimensional data here. So I have to satisfy a bunch of functions. I have to specify a bunch of functions. The functions with involving x3, x4, etc. are all kind of not relevant. So let's go ahead and specify the functions d0 and d1, which go from x1 to x0, and d0, d1, and d2, which go from x2 to x1. All right, so can someone tell me what is d0 of f? Remember, d0 is sort of recording the target of an edge.
It'll just be B.
Yeah, so then what's d0 of g?
C.
Yeah, and then d0 of h?
Also C.
Also c, all right. d1 of f?
A.
Yeah. d1 of g?
B.
And finally, d1 of h.
A.
Yeah. Okay, so that's good. We've now completely specified the functions d0 and d1 from x1 to x0. And now I just have to specify these functions from x2 to x1. So let me just tell you what they are. d0a is going to be g, d1a is going to be h, and d2a is going to be f. And that's a complete description of these three functions because x2 has only a single element. So I only have to say what these functions do to the element capital A. Okay, so why did I set d0g equal to g, d1 equal to h, and d2 equal to f? Well, first of all, let's note something. let's note that if I take d0 of d2 of a, I get the same thing as if I took d1 of d0 of a. And so there's some relationship between these functions defined from x2 to x1 and the functions from x1 to x0. So this is an example of one of those simplicial identities. And in fact, if I want d0, d1, and d2 to take, f, g, and h as their different values, it turns out to be only one way of assigning 0 to g, 1 to h, and 2 to f. That's the only way in which you can assign this function, which makes it satisfy the simplicial identities. Okay, are there any questions about sort of what a semi-simplicial set is, sort of formally?
So we shouldn't think of D0, D1, and D2 as, should we think of them as distinguished in any way?
Yeah, so it sort of turns out to be important that, D1, for example, on edges is recording the source and D0 the target. So there's something going on that we'll talk more about later about these aren't all sort of permutable. There's an ordering to these DI operations, and we're going to see more examples that will give you hopefully a feeling for what that ordering is saying. And another way of thinking about it is, it's important that when you walk around, say, the boundary of A, you go forward along G, backward along H, and then forward along F. So this ordering of forwards versus backwards is something that is going to have to be kept track of. I think hopefully some more examples will help with that. Are there any more questions about sort of just the formalism or definition of a semi-simplicial set? Okay, maybe the easiest thing to do is to go on and say some more words, and then I think you'll learn a lot just by working out some examples of semi-simplicial sets on the homework. So how do you compute the homology of a semi-simplicial set? All right, so if X is some semi-simplicial set, we let Sn of X denote the free abelian group generated by the set Xn of n simplices. So that's just what Xn is called. It's called the set of n simplices. It's one of the sets that comes in the definition of a semi-simplicial set. And so, just as we did with the directed graphs, we're going to be looking at the free abelian group on the simplices. Call that Sn of X. And now there's these boundary operators. So for every n greater than or equal to 1, there are group homomorphisms. Boundary n, which go from Sn of X to Sn minus 1 of X. And to define them, since they're group homomorphisms, we only need to say what they do to the generators of the free abelian group Sn of X. So a generator of Sn of X is just some element in Xn, and which that element should be sent to, will be sent to the sum from k equals 0 to n of -1 to the k dk of sigma, where that's that simplicial dk map. Okay, so this sign here, negative 1 to the k, is important, and it's distinguishing the dk with k odd from the ones with k even. That has something to do with how we walk around these simplices, and sometimes we have to walk over them backwards and sometimes forwards. All right, so as always, just please let me know if you have any questions. There's also just sort of a silly thing we can do. We can define the 0th boundary thing, which goes from the vertices in X, and we just send that to the 0 group. And so that's just the 0 homomorphism, the unique homomorphism into the 0 group. That lets us talk about the boundary of a vertex, and it's just kind of a silly thing. The boundary of a vertex is just 0 by definition. Okay, so definition. Suppose X is some semi-simplicial set. Okay, the group of n cycles in X, which we'll denote by Zn of X, is the kernel of this nth boundary operator. So it's exactly measuring, if you like, sort of potential loops in the semi-simplicial set X, but n-dimensional loops or n-dimensional holes. So that's the group of n cycles. And then we want to sort of get rid of the n cycles that are boundaries of yet higher dimensional things. So the group of n boundaries in X is going to be denoted Bnx is the image of the boundary operator from one higher dimension. So on your homework, which is why I recommend you sort of do these homework problems as we go along, it'll help you understand what's happening. You will prove that this boundary group is in fact a subgroup of Zn of X. So every boundary is a cycle. In other words, if you take the boundary of a boundary, you'll get 0. So that's a very important exercise. Okay, and then of course the Z of n is in turn, by definition, as a kernel, just a subgroup, again, of that Sn of X, which is that free abelian group on the n simplices. So these are the basic groups that we can attach to a semi-simplicial set. We have Sn of X, the free abelian group on the n simplices, Zn of X, the cycles or potential n-dimensional loops, and Bn of X, the boundaries or the sort of boring n-dimensional cycles, the ones that are actually boundaries of a higher dimensional object. Okay, so because of this homework exercise in which you prove that the boundaries are a subgroup of the cycles, it makes sense we can therefore define the homology of any simplicial set in dimension X, and it's just the cycles mod the boundaries. So this is a quotient abelian group. So as you hopefully know from algebra, if you have a abelian group and a subgroup, you can form the quotient group. And that quotient group is the last of the sort of fundamental groups will attach to a semi-simplicial set. It's Hn. So Hn of x is an abelian group by definition. And intuitively, it's going to measure the number of n-dimensional holes in your semi-simplicial set X. So you should think, roughly speaking, the number of generators of this abelian group is telling you the number of distinct, in some sense, holes in your semi-simplicial set X. Okay, so I know that's a lot of language. Hopefully it becomes clear, especially as you work on your homework and such. I think that gives sort of a complete answer to the problem of how we can generalize the things we said about graphs to the things that we want to say about higher dimensional objects. And then the next thing I want to talk about is how can we handle topological spaces instead of these combinatorial semi-simplicial sets. So are there any questions before I go on to topological spaces? All right, so then let's go on and ask the question, how do we get, so this is a new topic, how do we get a semi-simplicial set out of a topological space? So if you remember, in the first class, I gave you some examples of topological spaces like a circle, and I sort of extracted a semi-simplicial set by saying, oh, we'll just cut this up however we like. And it doesn't matter how we cut it up, we'll always get the same homology group. So we're going to go back and prove that there's sort of these nice finite ways of cutting up topological spaces and that you always get the same answers. However, it's going to take us a while to get to the proof of that statement. So what we're going to do instead is a little dodge. The first thing we're going to do is define for every topological space a canonical way of cutting it up into a semi-simplicial set. So maybe that's a bit surprising. What I'm saying is that there's always a sort of best or maximal way of turning a topological space into a semi-simplicial set. It's probably not very apparent from the kinds of ways we were turning a circle into a semi-simplicial set in the first lecture. So what's this sort of canonical way? That's what I want to describe next. And the basic tool that one needs to develop first is this notion of a standard n simplex. So for n greater than or equal to 0, the standard n simplex delta n is a subspace of Rn plus 1. So I'm describing here a topological space in the sense of 18901, and it's going to be given the subspace topology. It's going to sit inside n plus 1 dimensional Euclidean space, and it is the convex hole, which I'll say what convex hole means in a minute, the convex hole of the standard basis E0, E1 up to En in Rn plus 1. So what does convex hole mean? It means delta n is the set of linear combinations TI, EI, such that the sum of the TI is 1, and each of the ti are non-negative. So that's a subset of Rn plus 1. These are sometimes called barycentric coordinates, the ti. I'm going to draw some examples, which will hopefully make this a little bit clearer. So let's just draw some examples of the standard n simplices. So what is delta 1? So delta 1 is supposed to be a subspace of r squared. What does r squared look like? It has sort of two coordinate axes. And then maybe we can talk about the vector e0 and the point e1. This is what you might call 1, 0, and this is what you might call 0, 1. And now, what is delta 1? Delta 1 is this line segment here, connecting e0 to e1. So you should think of it as an edge, right? It's a segment or an interval, and it has a certain direction to it. 0 comes before 1 when we're counting numbers. Okay, so let me give another example, and then I'll ask if there's any questions. What does delta 2 look like in R3? All right, so here I have to draw carefully. So we're supposed to have 3 coordinate axes now. And so here's the point E0, here's the point E1, and now we have a new point E2. And so delta 1, or delta 2, sorry, is this triangle, this solid triangle here. So it's this 2-dimensional thing that you get by drawing everything. You draw the segments from E0 to E1, from E1 to E2, and from E2 to E0, but then you also shade in the interior. So these are, you know, topological spaces in the sense of 18901. They're big infinite objects. They have infinitely many points, etc., etc. Are there any questions about these standard n simplices? All right, so how do these standard n simplices allow us to define a canonical semi-simplicial set for any topological space? Okay, so definition. Given a topological space X, any topological space, we define sing n of X to be the set of all continuous maps from delta n to X. Okay, so sing n is just it's just a set. So it doesn't have any topology or anything like that. It's just a literal set. It's the set of functions from the topological space delta n to X. So you should imagine that this is incredibly huge. Okay, delta 0 is just a point, but sing 0 of X is the set of all points in X. So for something like the circle, that'll be an uncountable set. Right, the set of all points in the circle is some massive uncountable thing. So these are wildly infinite sets, but nonetheless, they're things we can talk about. Okay, so now I want to claim that these actually assemble into a semi-simplicial set. So there are maps sort of di, which go from sing n of X to sing n minus 1 of X, that come from if you like forgetting the basis element EI. So what do I mean by that? Well, for example, I should be able to define a function D1 from sing 2 of a space to sing 1 of a space. So if I have a continuous map from the 2 simplex into X, well, I can look at that. Okay, that has a point called E0 that's mapping into X, a point called E1 that's mapping into X, a point called E2 that's mapping into X, and I'm defining sort of a continuous map on the entire triangle. But in particular, since I'm looking at D1 here, I could just look at the edge from E0 to E2. I could just ignore the E1 vertex in the standard 2 simplex and just think about E0, E2, and the things connecting those. And that gives me a 1 simplex, which has a direction because 2 comes after 0 in the numbers. So I think it's worth thinking through what that means, that you can do this procedure of just ignoring one vertex and it gives you these DI maps, these simplicial maps. Okay, and so these make Sing of X, which is the collection of all these Sing n of X's, is a semi-simplicial space. So this is a semi-simplicial set. So this is some wildly infinite, crazy construction that you can do for any topological space. So we're dodging the problem of cutting a topological space into simplices by doing the maximal largest possible thing, where we just use all continuous functions from delta n to x to talk about the n simplices. So, okay, so I'll just remark that it's probably worth reading if this is confusing to you. Look at Hatcher's treatment of what he calls delta complexes. So there's a little discussion of delta complexes at the beginning of chapter 2 of his book. And delta complexes are just another name for a semi-simplicial set. Okay, so basically the entire world calls these semi-simplicial sets, and then Hatcher decided to call these delta complexes, and Hatcher became the standard textbook. And one of the many reasons I don't particularly love Hatcher's book is these random changing of names that don't make any sense. But in any case, we're going to call these semi-simplicial sets because that's what, say, every research article would call these. But just keep in mind that if you see the word delta complex, it means the same thing. And it's probably worth looking at some of the pictures that Hatcher has of delta complexes that can help you build some intuition. And also you can just Google around for semi-simplicial set or delta complex, and you'll see a lot of online sources that are discussing these things, and that could maybe help. Okay, so let me just say now that if X is a topological space, we can define Sn of X, Cn of X, Dn of X, and Hn of X to be just Sn of Sing X, Zn of Sing X, Dn of Sing X, and Hn of Sing X, respectively. So all we're doing is establishing some shorthand so that we don't have to continuously write Sing everywhere. Homology, cycles, boundaries, all these things are really things you attach to a semi-simplicial set. But now, because of this Sing construction, we have a way to also attach them to topological spaces. So we can talk about talk about all these objects for topological spaces. So you should really think that we have now these transformations, topological spaces. This goes to semi-simplicial sets. In turn goes to abelian groups, right? Where this is Sing. Yes, Sing X is just the semi-simplicial set formed by all the Sing NX. That's exactly right. There's a question in chat, and then this is maybe like one of these nth homology groups. So there's a sort of hierarchy here where this is something, geometric. You can transport it into something combinatorial. And finally, you get down to something algebraic. Okay. So, all right, maybe rather than jumping into a new topic, since we have only 4 minutes left, I'll stop the class here for now and just ask if there are any questions. I will be hanging around in the Zoom for the next hour, so if you want to pop in at all to have office hours, I'll stop the recording here.